All right, so in the previous video, we were learning how line integrals can be used to find work in a vector field, in a force field. And the example that we used was, this was the vector field, and we found that this particular force field was conservative, right? We showed the conservatives, and if you recall, in that previous example, there was some particle moving from 0, 0 to 1, 1, only it was going through different paths, right? We evaluated different paths. Now, I need you to recall that when we say conservative vector field, that means that there is some potential function out there, right, whose gradient is equal to the vector field. Now, we spent time in 15.2 going through how you would, or 15.1, I believe it was, going through how it is that you would figure out what that potential function would be. You just know that if it is a conservative vector field, that we are guaranteed to have one, right? So using the procedures that we used back in 15.1, we could figure out that the potential function for this vector field is 1/4 x squared y. Now, please don't lose this next point. Okay, listen, if you go back and you look at the procedures we used in 15.1, I guarantee you could figure out how, using those techniques, we could get that potential function from the vector field. Please don't let me lose you. Here is the critical point of this entire section. Remember, we were moving from one point to the next, from 0, 0 to 1, 1. Now, in the equivalent of doing, and this is just the f, just remember how you could do f of x sub 2 minus f of x sub 1, right? This is kind of back in single variable calculus. What we're going to do is, let's just notice something. What if you f of the second point minus f of the first point? And here it is. So here's that potential function for that conservative vector field. 0.2 minus 0.1. So f of 1, 1 minus f of 0, 0. Well, that's 1/4 times 1 squared times 1 minus 1/4 times 0 squared times 0 is just 1/4. Amazing enough, that is exactly what we got. Remember, 1/4 is exactly what we got going through all of that line integration. We got the same thing, just evaluating that conservative vector field for those points. And that is the gist. That is what we call the fundamental theorem of line integrals. And it's basically we have to assume that your curve is some piecewise smooth curve lying on an open region, right? And we go back to, we have to assume that your vector field is a conservative vector field. But once we have those assumptions, we can find the work done by simply using that potential function for that conservative vector field, and it just evaluating that potential function at over the intervals, right? Or at at the points if you happen to have the points. This part right here is exactly what I did on that previous page. This is the f of 1, 1 minus f of 0, 0. Okay. The proof of this is shown if you'd like to go through it. My sincere apologies for this mad rush at the end of this this chapter, but alas, I've run out of time. The only thing that I want to do for 15.4 is I at least want to introduce Green's theorem. All right, so I will not test you on 15.4. So at that point, what do you do? Do you just press stop? Stop the video? That's okay. I get it. But I won't test you on 15.4. Maybe I should have waited till after. No worries. But look, this is a I always try to make it to Green's theorem before I end Calc 3. Don't always succeed depending on various circumstances. In this particular semester, I will at least just introduce it. Let me just tell you, it's just a time-saving tool. It's a time-saving tool that for calculating line integrals. It just certain conditions have to be met. That's all it is. The conditions are so when we say simply connected region, right? Remember that region R. When we say it's a simply connected region in mathematics, what we mean is that the curve doesn't cross itself if you were to trace it out by a vector function, right? You could. It's probably better to show you what is not simply connected. So if you have regions that have holes in them, that's not simply connected. Green's theorem's not going to work. If you have a region that is separated, Green's theorem's not going to work. But if you have a region that is simply connected, Green's theorem can help you look. It helps you take a line integral and turn it into a double integral. And double integrals are something we've practiced a lot, right? Hence, now it's possible I could throw an extra credit, I guess, on Green's theorem, but it is just the double integral. And notice we're taking the partials here. We're taking the partials of n with respect to x. We're taking the partials of m with respect to y, and it is an extremely important theorem. And the mathematician George Green, just to kind of let you know, when you first started calculus, we were 400 plus years back in history. I think George Green probably in around the 1820s, 1830s maybe published the paper. But so you are moving in the right direction. But that's the gist. You know how to do double integrals. So for example, if you wanted to, if you didn't want to evaluate this with a line integral, you would just have to make sure the conditions are met, that it is simply connected, continuous. And you could see that if you're going, if C is the path from 0, 0 to 1, 1, it's basically being traced along this path. This is from 0, 0 to 1, 1. It's along the path y equals x cubed. And then this is the path that it would take as it goes from 1, 1 back to 0, 0. You can see that it's simply connected. There's no split regions. There's no holes in the region R. So you can use Green's theorem to evaluate this line integral, right? And I mean, it's quite, all you would need is you would label m in this case would be y cubed, and n in this case would be x cubed plus 3xy squared. And you just need to take these partials, right? Take the partial of n with respect to x, take the partial of m with respect to y. What do you get from that? Well, if you were to, this is that partial of n with respect to x. This is that partial of m with respect to y. Now, notice I haven't set up my bounds because I haven't chose my order of integration. But because these y squareds are going to cancel out, leaving me with just 3x squared. We want to, we are forced to go, well, we want to go dy dx, right? Because this is really easy. Well, it's not bad to integrate with respect to x either, but it is just much easier if you just integrate with respect to y. If we're going to go dy dx, then let's start with our x bounds, our constants on the outside, right? So dx would be from 0 to 1. And now, remember, you had the equations on where it was y equals x and y equals x cubed. But when you get to dy, you're going to have to solve for y. So in other words, did I write that correctly? Y equals x cubed, y equals x. Oh, my sincere apologies. I was thinking we would have to switch up the bounds of integration. But no, we don't. It was already defined in terms of y. Y equals, yeah, so we're going from x cubed to x. Right, that makes perfect sense because it has to be above x cubed but below x. Yeah. Okay. I was thinking for some reason I guess I'm in a rush. I was thinking that we were going to have to that we had to switch the bounds in this problem, but we didn't. So okay. So now that we have everything set up, you know how to do double integration, right? This is not bad. So our double integral is 0 to 1, 3x squared y from x cubed to x. Plugging back in for y. We've got 0 to 1, 3x cubed minus 3x to the 5th dx. One more round of integrating, and you get 1/4. So this would have been a little bit tougher if you would have did this using a line integral, but you were deciding to employ Green's theorem did save you some time. I will not test you on 15.4 one more time, but if you decide to use this time-saving technique for a problem that I do give you, that's no problem. As always, it could show up on an extra credit because anything could show up on an extra credit. You guys take care.